Well, good day, guys. Let's do some graph analysis problems today. In particular, this is going to be problem 3 on your problem set. Now, this would have been a problem that your graphing calculator would not have been allowed. So we're going to do all of this as if we did not have a calculator with us. And as all the non-calculator problems are, in fact, as all the free response problems are, if you find that you're doing super complicated arithmetic or super complicated algebra, you're probably doing the problem wrong. Okay. This is about understanding some key concepts and knowing how to describe them and apply them concisely but accurately. Okay. So let's read the prompt to this one. There's a graph. First of all, let's notice there's a graph made up of line segments. Well, except for this curious shape here in the middle. Now this is going to be described in the prompt as a semicircle and 3 line segments. And that is going to be the graph called f, or f of x. Now they're going to define function g this way. And g is the definite integral of this function starting at the lower limit -3 and upper limit is x. Okay, now note -3 is not the very left end of this graph. -3 is actually right here, guys. Okay, so -3 starts right there. So let's actually just dig into the parts here. And then at the end of the video, we're going to show you the full answer key and talk about where the points were awarded. Okay, again, I want to emphasize this. Your goal in the free response problems is to find as many places to earn the points as possible. You certainly are not expected to earn every point to get a perfect score on this exam, guys. And I want to point that out again. You can find even if there's 4 parts, if you can even find 2 of the parts to do really, really well and earn all the points on, that's better than a lot of the students taking the exam. Okay. Now, here we have, it says find g of 0 and g prime of 0. Well, let's just go and look at the definition of g again. G of x was the integral from -3 to x f of t dt. So g of 0, we can just fill in 0 for x into that definition. It's going to be the definite integral from -3 to 0 of f. Now, if we had an equation for f, we just use the fundamental theorem of calculus and evaluate this integral, but we don't. We have the graph of f. Hence, we're in the graph analysis type problem here. So we have to evaluate this integral from the graph. So your main tool is to interpret this integral as the area under the curve or under the graph. So I'm going to take my highlighter and I'm going to shade in starting from -3. Okay, so this integral starts at -3 and then it's going to go in this case to 0. Okay, so I'm just going to take my green highlighter and I'm going to highlight this all in here. So your best bet is to interpret this integral as the area that I just shaded in, which happens to be a trapezoid. Although I'm guessing a lot of students would probably just divide this up this way now into maybe a rectangle and a triangle. So this point was 0, 1. So this little lower rectangle was 1 unit high and 3 across. That's got an area of 3. And then this is now also a height of 1, because the point has a height of 2. So it's 1 across and 3 high. So this area is 1.5. And so therefore this is altogether 4.5. Okay, final answer to that part. Now g prime is actually even easier because remember we're finding the derivative of this function g. This is where we remember the fundamental theorem of calculus, the second part, and we're actually going to write just g prime of x first to remind you that g prime of x is now the derivative of this integral. And there's an important theorem here that says the derivative of this integral leads back to the original integrand, and it's now a function f of x. So the quick answer to this one for g prime of 0, it's the same as f of 0. And that can be read right off the graph. The graph contains the point, the graph of f contains the point 0, 1, so f of 0 is 1. Therefore, g prime of 0 is 1. That's the final answer there. Okay. So once again, not a lot of complicated arithmetic. You just have to know those two important concepts, that the integral needed for g of 0 is going to be interpreted as area, and that the derivative of g requires you know the second fundamental theorem of calculus, meaning the derivative undoes the integral, you're back to function f. So f of 0 is 1, and that's the value of g prime of 0. Part B says, find all the values of x in the open interval from -5 to 4. Now that is the entire domain of the graph, -5 to 4, in which g attains a relative maximum. Justify your answer. You're going to have to explain your answer to get the points here. Okay. Now, normally, when we would have discussed relative max and mins in our course, we would have given you an equation of the function and said, where does it have a relative maximum? And your test for that is its derivative has to change signs. Now it has to change signs for there to be a maximum from a positive derivative to a negative derivative. So what we want to find is we want g prime to change from positive to negative. Okay, well, again, g prime is what we need to study, but we have g defined as this integral. But something we did in A reminds us how g prime is done. G prime is simply f, and f is the graph that we're given up there. So what we really want to do is say, when does f change signs from positive to negative? And that's an easy thing to spot. This is the graph of f. Okay, so the first section of the graph is on the negative side of the, it's being graphed with negative y values. So the graph of f is negative here. Once it crosses through this point -4, 0 on the interval from -4 really all the way to 3, the graph is either positive or just briefly at one point 0, but it never changes it back into negatives until it gets to here. Okay, so the graph of f is negative, then it goes positive all through here, and then once it gets to x equals 3, it's now crossing through and becoming negative again. And so this occurs at only one point. Okay, so the value of x is 3, and the justification is that g prime, which is also known as f, changes from positive to negative. Okay, so we really didn't have to write any of this over there. This was just for ourselves as we were thinking it through. The justification is what I'm going to put the box around right now. And so really the answer -3, and this brief little justification, that's all it would take to get full points again. Let's go on to part C. Part C now is asking us to find the absolute minimum value of g on the closed interval -5, 4. Now that's different. That's a different thing than a relative minimum or a relative extrema that was asked for in B. An absolute minimum, if it's asked on a closed interval, remember this reminds us that we're probably going to want to use the candidates test here and include -5 and 4 as candidates. Okay, let's actually make a list of our candidates here first. Automatically -5 and 4 are candidates because they are the first and last point in the interval. Something we did in part B also gives us the other two candidates. Remember, candidates include also any time where the derivative of our function is equal to 0. The derivative of g is function f, whose graph is given, And it's easy to tell when f is equal to 0. It's at -4 and it's at +3. So they become the other candidates. Now, something we learned in part B was that at x equals 3, there was a relative maximum point. We probably can just rule that out then as any possibility of being the absolute minimum spot. So I'm just going to rule that out right now as one of our candidates. So we do have to now, to perform the candidates test, we just have to evaluate the function at those 3 other points. So g of -5, and then we'll take g of -4, and then g of +4. Okay, now in each of these, we'll use the definition of g as a definite integral from -3 to your x, which in this first one is -5. This one will be to -4 from -3. This one will be from -3 to +4. All right, so we'll interpret these integrals as area just like we did in part A, right? So I'm going to take my highlighter and we'll shade in what we would use as the integral from -3 to -5. So -3 starts right here. It goes all the way to 5, so that means I'll be shading upwards a little bit there, and I'll be shading this part there. Now notice those are 2 triangles that have the exact same area. You know, even though this integral does go from right to left here, from -3 to -5, the areas are going to negate each other regardless. And so our answer to this is going to be 0. Okay. Now for our next one is from -3 to -4. So here is -3 again. -4 is the point of intersection. So we really just want the area of this upper triangle. Now this has a width of 1 from -3 to -4, and it's got a height of 2. So the area of this triangle is 1 square unit, but that's not the value of this integral. It's because this integral is going from right to left. So even though the area is 1, this integral has to be the reverse of that, which is going to be -1. Okay, and that has to do with, again, the integral that we've got written is actually got the lower limit bigger than the upper limit. Okay, so that is making the value the opposite of what the shaded triangle's area is. And I think g of 4 is the toughest. You really earn your point with this one. You've got to shade in all the way from -3 all the way up here to 4. Okay, so I'm going to use the green this time and shade this in. Somebody upset the dog, didn't they? All right, here we go, guys. Let's shade this in. Now, we got help from part A here because this has an area. This part we found in part A to be an area of 4.5. 4.5. So now what's left is to find these other oddly shaped sections here. And let's start with this. This is a triangle. That'll be a 1 by 1 divided by 2. So far we've got 4.5. This triangle is going to be another 0.5. Now the best way to take this part underneath the semicircle, I think the easiest way would be to just to think of it as a rectangle and then just subtract out the semicircle, right? So that rectangle is actually going to have an area of 2. And then this circle has a radius of 1, okay, because here's the center of that semicircle. The radius is 1, and so the area of an entire circle would be pi times 1 squared. Okay, so think about through here. That means the area of the semicircle is pi over 2. Okay, and so filling that in down here, I'm going to have 4.5 plus a half, which is 5, plus 2 is 7, minus pi over 2. Now, it's asking for what the relative minimum is. So honestly, you know, you never do have to completely evaluate expressions here, but you need to determine which one is the smallest. Well, between 0 and negative 1 is smaller. So all I've really got to do is convince myself that maybe that this final one is bigger than either of those. So that would make negative 1 the minimum. I believe it is because pi over 2 is just barely bigger than 1. So this is going to be for sure a positive answer here. So the absolute minimum value is going to be negative 1. Okay, so negative 1 is the minimum value. Okay, so the justification was we identified all the candidates, we evaluated G at each of the candidates, and then figured out which of those values was the smallest, and it was G of negative 4, which is negative 1. Okay, now, important to note, the answer is negative 1. The answer is not the x value, which is negative 4. It says find the minimum value of G. So the minimum value is the value of this integral, negative 1. It's not asking at what value of x is the absolute minimum. It's asking what the minimum value of the G function is, and that's negative 1. Okay? That's an important distinction because I guarantee a lot of students who could answer all this part right would get the answer point wrong because they stated that negative 3 is, or sorry, they might state that negative 4 is the answer. But that's a value of x, not a value of the function. Okay? So part D, find all the values of x in the open interval negative 5, 4, at which the graph of G has an inflection point. So a little throwback again to the study of derivatives. So things we've already gotten figured out from the previous parts. G is this integral. That's G of x, okay? We figured out that G prime is the same as f of x. Now for inflection points, you have to know that inflection points are found using the second derivative of your function. So we need G double prime. And guys, that would be then the derivative of f. I encourage you just to pause the video for a minute and think back to your study of derivatives and how does the second derivative of the function indicate that there's an inflection point? Okay, well, what you studied there was that an inflection point occurs when the second derivative has to change signs. So I'm going to make a note of that here. G double prime must change signs. Okay, well then, okay, that's not obvious from the graph because the graph is f. So if we actually go to our notes here, the second derivative of G is really the first derivative of f. So what I'm going to look for in my graph is when does f prime change signs? And f prime is interpreted to be the slope of this graph. So what we want to find is when the slope of this graph changes from positive to negative or negative to positive. Or if you want to state it again, it would be when does the graph of f change from increasing to decreasing or decreasing to increasing? Let's just erase some of this other writing so we can see it all clearly again. And this time, this graph goes increasing to decreasing here at negative 3. It decreases all along this line segment. It decreases along the first part of the semicircle. Then it changes to increasing. So I've got another spot right there. It increases along the last part of the semicircle, then sharply changes to decreasing. Now there are sharp points at 2 of these, but that does not matter. The function we're looking at is continuous. Okay, and so that's all that has to be true there. So it happened 3 times at negative 3, at 1, and at 2. Interesting note about this one. This is a rare time when it's only asking for the values of x. There is no mention of having to justify your answer. So we didn't even have to state how we found them. Okay, you'll see that in the answer key. Let's look at the answer key for all 4 parts. Remember, every problem is worth 9. And this time, part C was worth the most, probably because of the calculation needed in the candidates test. So part A, just 2 points, 1 for the value of g of 0, 1 for the value of g prime of 0. You know, you honestly probably didn't have to even show your work for this. If you did all the math to figure out the area of that shape and just stated the answer, probably going to earn you the point. G prime of 0 was f of 0, that was 1. Part B, it's worth 2 points. 1 for noting that the value was going to be at x equals 3. The other one for noting how you found it. It was when the derivative of g, otherwise known as f, changes from positive to negative. Part C is worth the most points. Remember, you're finding the absolute minimum. So the first point is earned if you identified -4 as an additional candidate other than the endpoints. Second point is for evaluating g of -4 to be -1. Now, the last point is all of the other justifications, such as evaluating the function at the other 2 candidates, and then making the proper conclusion that -1 was the smallest of all of those. Okay. And D, simple. It's actually 2 points though. You get both points if you have all 3 correct values and no additional points, okay, or not missing any. So 2 points for the correct values. Now it says we're going to deduct points if you're missing any of them or have any extra ones. So here's an example where maybe if you had 2 of these 3, like maybe if you had -3 and 1, but then had 2 other numbers that were both wrong, you actually would get 0 points for this, okay? Because you would get -1 for each of the wrong points you wrote, okay? Well, hope this helps you guys, and we will keep putting videos out like this until next Tuesday for the other problem topics. Wish you guys luck as you continue to study and review for your exam.